Okay, so here we have a question that says, is the following equation true? And it reads 2 to the fourth. Does that equal, they're asking, 2 to the third plus 2 to the third? And then, of course, can you explain why, and can you explain this connection for any a to the x value? What's great about this question, I think, is that um, we're looking at the laws of exponents through addition. It's often looking at combinations of multiplication and division, but we forget that there is a connection between exponents and addition as well. And here also we're looking for general patterns, right? We're looking for the laws that allow us to show these things are equal, and the laws that allow us to basically play around or tinker with this problem until we're able to come up with some kind of general algebraic formula. So let's do that. Is 2 to the fourth equal to 2 to the third plus 2 to the third? Well, 2 to the fourth is 16, right? 2 times 2 times 2 times 2, and 2 to the third is 8. And so is this 2 to the third. So yeah, it's true, right? 16 does equal 8 plus 8. It works. So now the question is, why might it work? Well, let's just think about this for a moment. Let's take 2 to the fourth, and let's break it up in several different ways. Using one type of law of exponents, which says that if you have any number to a power, and then you multiply it by the same number, the same base, to a different power, or the same power, it's equal to that number plus the sum of the powers. So for example, if I take 2 to the first and I multiply that by 2 to the third, what I should get is 2 to the 1 plus 3, or 4. And that works as well because 2 to the first is 2, 2 to the third is 8, multiply 2 and 8, and that's equal to 2 to the fourth, right? 16 is equal to 16. So this law right here is going to help us explore different ways of breaking up 2 to the fourth. For example, it could be equal to what we just showed. It's the same thing as 2 to the first times 2 to the third. So we're just now going to find different combinations, right, where the base is 2 and the exponents add up to 4. So we have 1 and 3, or 3 and 1, same thing here, but we don't have 2 squared times 2 squared. And then 2 to the fourth can also be seen, right, as 2 to the, 2 to the third, 2 to the 1, but I guess 2 to the 0 times 2 to the 4. So you have these three combinations to look at, right? And here, probably the one that helps us out the most, or is almost immediately you can see that these two, this one and this one, are connected, right? And here's what I mean. Let's just think for a moment about what this equation means. Specifically this right here. So we're going to keep expanding or breaking this down. Usually the investigation stops there, but we're going further. 2 to the first times 2 to the third. Well, what does it mean to say 2 to the first times 2 to the third? Well, that means to me, since 2 to the first is 2, it means 2 times 2 to the third. And what does that mean? Let's keep going. Well, when you multiply anything by 2, what does that mean? So for example, if I have 2 times 3, what does this mean? Well, one way to look at it is say you have two groups of 3. So it's 3 plus 3. If I have 2 times 4, that equals 4 plus 4. So it's two groups of whatever you have here. And it could be anything. So here I have two groups of 2 to the third. So instead of 3 plus 3 or 4 plus 4, I'm just going to say that 2 times 2 to the third, that's like two groups of 2 to the third. So 2 to the third plus 2 to the third. Just following that pattern here. And look at that. That's exactly what we started with up here, right? So we can justify these two things are equal by using this law of exponents, look at different combination, right, of ways to break up 2 to the fourth. Here we highlighted this one combination and just basically used our definition of multiplication to rewrite it in a different way. And it shows they're equal. But can we extend this to anything, right? Well, I think we should change it up a little bit. Here we dealt with 2. Let's try working with 3 for a little bit and see if that helps us. So let's say we have 3, right? Not 2 this time, but 3 to the fourth. Well, first of all, what does that number equal? Well, it equals 3 times 3 times 3 times 3, right? 4 threes. Now 3 times 3 is 9, times 3 is 27, times 3, right, is, well, 3 times 20 is 60, 3 times 7 is 21, that's 81. So that's the number we're working with here, is 81, or 3 to the 4th. How could we break this up? Well, 3 to the 4th can be thought of course, as 3 to the 0 times 3 to the 4th, which is equal to 1 times 3 to the 4th. But keep going, 3 to the 4th could also be thought of as 3 to the 1st, right? I'm going to raise the first exponent and then lower the second, times 3 to the 3rd. And then 3 to the 4th could also be thought of as what? Well, 3 to the 2nd times 3 to the 2nd, and we could keep going here. We get 3 and 1 again, but we've already dealt with that one. So let's move on. Let's move forward here. Okay, so what will each of these mean, right? Well, let's start with the middle one here. 3 to the 1st times 3 to the 3rd. It kind of reminds me of the last problem. Well, 3 to the 1st is 3. So this is going to mean 3 groups of 3 to the 3rd, right? So it's just 3 times 3 to the 3rd, and that's equal to 3 to the 3rd, right? The first group of 3 to the 3rd, plus our second group of 3 to the 3rd, plus our third group, right? That's 3 27s, or 81. So we can rewrite this. And take note, we took 3 to the 4th, and that ended up equaling 3 to the 3rd plus 3 to the 3rd plus 3 to the 3rd. So that's our first combination. 2 more to go, and I think we'll be on the right track. Next here, we have 3 to the 0 times 3 to the 4th, which for me is just one group, right? 3 to the 0 is 1. Well, use a different color here. 3 to the 0 is 1 times 3 to the 4th, which we already established is 81. So that makes sense. It's one group of 3 to the 4th. So in other words, 3 to the 4th equals itself. And last, but not least, we have 3 squared times 3 squared. So 3 squared is 9. So this is like 9 times 3 squared, which means 9 groups of 3 squared. 3 squared plus 3 squared plus 3 squared, right, and so forth, 9 times. So what's happening here? How do we extend this? If we have a to the x power, let's use a different color, right? A to the x power. What will this equal in terms of a? Well, what I notice immediately is that if I have 3 to the 4th, right, we'll start with this one right here. That's going to be the same thing as 3 to the 1st times 3 to the 3rd. And I notice right away that if I add our two exponents, that's a law of exponents, I get 4, or the total. So in this case, a to the x, if I break it up into two terms, if we add the exponents, we should always get x. Right? Notice each of these, 2 and 2 is 4, 1 and 3 is 4, and 0 and 4 is 4. It's based on our laws of exponents. And the next thing I notice is, in this case, I have one group of 3's times 3 groups of 3's. So that's, right, 3 to the 1st times 3 to the 3rd. And also, that just means, well, notice my base never changed, right? I start with 3, I'm rewriting it in terms of a base of 3. So here we have a base of a, right, times another base of a. Notice how it happens each time, 3 times 3. Here we're going to have 8 times a. So the first number, in the order I wrote it, think about it this way. If I took this exponent minus this one, or the reverse, the original exponent minus this one, I get this exponent. So 4 minus 4 is 0. And the next one, 4 minus 3 is 1. And the next one, 4 minus 2 is 2. So what do we do? What happens here? Well, here we start with a to the x, right? And then we're going to pick some number. Let's say y. And here, this exponent is going to be always x minus y. And that's our general formula here to kind of express how this might work, how these things are always equal. And all this is saying now is what? Well, if we look back at the numbers here, I know there's all kinds of things written down. And I'll go back to the middle group here. 3 to the 4th equals 3 to the 1st times 3 to the 3rd. This means you have 3 to the 1 groups of 3 to the 3rd. You could read it the other way. It doesn't really matter, but I'll read it this way. You have 3 to the 1 groups of 3 to the 3rd. In the other case, we have 3 squared times 3 squared, right? This means you have 3 to the 2 groups of 3 to the 2. So here we can read that this says you have a to the x minus y groups of a to the y. And that's always going to mean the same thing, right? Here, here, a to the y plus a to the y plus a to the y, and so forth. We're going to keep adding a to the y. How many times do we do it? Well, the operation that connects these two variables is multiplication. And remember, in each case here, like 3 to the 1 times 3 squared, that means 3 groups of 3 squared, or 3 groups of 3 to the third. So we literally took 3 groups of 3 to the third and added them. In the next one, we have 3 squared times 3 squared. So that was 9 groups of 3 squared, so we added 3 squared 9 times. Here, right, we have a to the x minus 1 groups of a to the y. So here we're going to have a to the x minus y groups of a to the y. It's just following that idea all along. So there is some way to express what's happening, right, that connects your original a to the x and this right here. And you might be able to extend it even further. The goal is that, this algebra can be perceived as very complicated, but it might simplify the process. It gives us a way of saying, yes, that's going to happen, right? This pattern where we can add. And it's always going to happen in this way. So essentially, we're looking at almost another turn or another development of the laws of exponents. All right, hope this helped.